This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Morgan, you've emailed everybody or something? Okay, so anyway, that's apparently not going to be on some other schedule, but that's what has now been arranged. So I just want to talk today informally in a way, because I want you to be able to think about some of these things. I'm just going to finish up where I left off to remind you that if you I turned the problem around. We looked at a problem in which the shock was steady and we had supersonic flow coming in and subsonic flow going out of the shock. And if you turn the problem around and you have a shock wave propagating into a fluid at rest, then we can use, if it's a steady flow, we can use the same results, because you can get one from the other by just a Galilean transformation or subtracting the velocity of the shock. And then it's stationary, and then you could work out for that case what the velocity, what the Mach number is behind the shock. And the shock wave, of course, increases the temperature as well as giving you a velocity behind the shock in the direction of the shock wave. But because you're increasing the temperature, you're also increasing the speed of sound. And the maximum Mach number you can get behind an infinitely strong shock is only 2, the square root of 2 over gamma into gamma minus 1, which, as I mentioned last time, for gamma 1.4 was 1.89. So if you had an infinitely strong shock, for example, from a nuclear explosion, then the Mach number behind that shock relative to the ground is only 1.89. But the pressure rise is huge, and that's, of course, those of you who've been to Hiroshima, and I encourage all of you to visit there sometime in your life. It will affect you for the rest of your life, just how intense that shock was. And I can tell you that my wife and I were there, and a Japanese man came up to us and said, "Come with me, I'd like to show you something." So he took us to a cemetery, but the cemetery was immediately, it was called at ground zero, so it was immediately below the explosion. This explosion in the atmosphere was, I think, at about 5,000 feet. Anyway, what he asked us to do was to feel the top of the gravestones. These are gravestones made of granite. And you felt the top of the gravestone, and it was extremely rough. And you felt the side of the gravestone, and it was extremely smooth. And you don't need to think for long about why that could be the case. On the top, of course, if you're at ground zero, you were in the direct radiation. So the intensity was so high that it melted the quartz. The quartz evaporated, and that's why it's rough. And the sides, of course, the projected area is much smaller, and so it remains smooth. Anyway, that's very much an aside. So then what I wanted to do today was to talk about small amplitude disturbances in general in a fluid like salt water. So you'll recall that one of the important results I obtained was that the difference in entropy behind this shock was related to the pressure difference, and there's only that pressure difference is a compressive shock because the entropy has to increase, then it depends on d2v dp squared, and for a perfect gas, I showed you that d2v dp squared was simply gamma plus 1 over gamma squared v over p squared. And so if you put that in if you put that expression into this expression, then you can see that v would be RT over p, and so the t's will cancel and you'll divide by an r and you're left with a p in the bottom, and so you get something dimensionless. S2 minus S1 over r is 1 over 12 gamma plus 1 over gamma squared delta p over p cubed. And that's important because it says that the change in entropy is third order in the relative change of pressure across the shock. So if you assume that you're going to talk about very small amplitude waves where delta p over p is going to be much, much less than 1, then because this is third order in that change, this is extremely small, and we can assume that S is constant. So that's the basis of acoustics, where we're going to say that P minus P naught over P naught is much, much less than 1, and rho minus rho naught over rho naught is much less than 1, and U over the A naught is much, much less than 1, and we'll see why these two are like they are in a minute. So if you say, well, from my canonical equation of state, I can get P as a function of the density and the entropy, but I'm going to hold the entropy constant, so P minus P naught to first order will be dP d rho at fixed entropy, rho minus rho naught. And this dP d rho at fixed entropy is something that you'll remember that I called A naught squared, and I didn't explain then really why it's what A naught squared has to do with the speed of sound, and we're going to do that now. But we're going to say that that's A naught squared, and so this expression here is P minus P naught is to first order A naught squared rho minus rho naught. And so if I say that P minus P naught is rho prime, P prime I mean, and rho minus rho naught is rho prime, then this expression here simply means that P prime is A naught squared rho prime for small fluctuations. So now let's look at the general solutions for the equations of motion. So you'll recollect that I worked out for you conservation of mass, and it was this equation here, and conservation of momentum was this equation here. Rate of change of a density plus the divergence of a flux was equal to 0, and this includes the pressure but the absence of the viscous stresses. And this equation, when you subtract out continuity, can be written as an Euler equation where this is rho du dt plus rho u dot grad u, and this becomes minus dp dxi, and then vector notation is like this, minus the gradient of the pressure. And for rho minus rho naught is equal to rho prime, and P minus P naught equal to P prime, and rho prime over rho naught is much, much less than 1, so rho naught is a constant. When you put that into this equation...
So okay, that first line is mass conservation, so how did you get to the second line?
The second line is conservation of momentum.
Oh, okay, yeah. All right.
Conservation of momentum. Those equations, you must remember those equations in words. It's rate of change of density, in this case the momentum density, plus the net flux out of the momentum density, but I have to include the pressure, and I include it in this way, and you'll see that I have I've written that many times before, and that's equal to naught. All right, so now we're going to assume rho prime and p prime, and rho prime over rho naught is much, much less than 1, and p prime over p naught is going to be much less than 1. In other words, it's isentropic. Then our equation for d rho dt, the first equation, if I just substitute for rho prime, rho minus rho naught, or the density is rho naught plus rho prime. Rho naught's a constant, so d rho dt is only going to be d rho prime dt. And then this equation for...
What's P naught in this instance? The mean or the second?
P naught is just the reference absolute pressure in an ambient fluid at rest. P naught is the ambient fluid, the undisturbed pressure. And rho naught is the undisturbed density. So in this equation here, we're going to write rho is equal to rho naught plus rho prime. So we'll have rho naught times the divergence of u plus rho prime times the divergence of u. And then I also, since there's going to be a gradient in density, I'm going to have this, if you expand it out, will be u dot grad rho prime equals naught. So that equation, that's all the terms that are in it. And you can see that if you divide by rho naught, this term's going to be small compared with this term here. So we're going to look at that now, but I'm going to now do the second equation, which is the momentum equation or Euler's equation. So I have rho naught du dt plus u dot grad u, and then plus a rho prime du dt plus u dot grad u. Well, this is obviously a bigger term. And that's minus the gradient in pressure, which is minus A naught, and the pressure is P naught plus P prime. So the only one that varies is P prime. So it's minus the gradient of P prime, which is minus A naught squared, the gradient of rho prime. All right. So now, in that first equation, I'm going to make some estimates. So let's see how I do that. Actually, I'm going to do it in this equation here, or this equation here. I'm going to make some estimates in this equation here. So here is the equation for momentum, which is really just the Euler equation, and here it is written here. And I've divided, in order to get to this equation, I divided by rho naught, so I've got the gradient of rho prime over rho naught, and I divided the left-hand side by 1 upon A naught squared, and then I've got this inside here. So now, I'm anticipating wave-like solutions. So if you assumed a wave-like solution, u was u e to the I kx minus omega t. I think you will have seen in other courses the idea of a wave is e to the I kx minus omega t, where the speed of the wave is omega is 2 pi f and k is 2 pi over the wavelength. So the speed of the wave is f lambda, which you would know from high school. And that's also equal to omega over k. So we're going to make some estimates in this equation here. So the ddt is going to bring out an omega times u, and the u dot grad u is just going to be u ddx ddy ddz of this right-hand side, which is going to be of the order of k. It's going to bring a k out, e to the I kx minus omega t. So when you do that, you make orders of magnitude of estimates. So this 1 upon a naught squared du dt gives me omega u over a naught squared plus u squared over a naught squared, and this d dx or d dy is going to bring out a k. And on this right-hand side, I'm going to have the gradient of rho prime that's going to bring out another k for a wave-like solutions, rho prime over rho naught. So if I divide by k everywhere, I have omega over k, which is equal to a naught. So that cancels one of those. So I have u over a naught is of the order of this right-hand side, rho prime over rho naught, just as we found for the weak shock wave solution. And this term, which came from here, is clearly a u naught over a squared, so it's a rho prime over rho naught squared, so it's a second order term. It's not the first order term. So that's a very important insight. So u dot grad u is a second order quantity. And similarly, if we go back to equation 1 and look at all of those terms and do the same sort of trick for looking at wave-like solutions, we have omega times rho prime, omega times rho prime, and then I have rho naught, and the div u is going to give me a k times u, and then a rho prime and a k times u, and then that u dot grad rho prime gives me this uk rho prime, and that's equal, or that's of the order of. So if I divide this by k, you can, and by rho naught, you can see that I'll have a rho prime over rho naught, and dividing this by k, I'll have an omega over k, which is an a naught. So if I divide that by a naught, I'll have rho prime over rho naught plus u over a naught. So thus, and these two terms here are negligibly small. I have a rho prime over rho naught and a u over a naught, and they are second order quantities. So the original mass and momentum equations become, once I, so to speak, linearize, throw out the higher order terms, I have only this much left from conservation of mass, d rho prime dt plus rho naught div u equals 0. And from the momentum equation, I have rho naught du dt, the u squared term, we're going to neglect u dot grad u. And then I have a minus a naught squared, the gradient of rho prime. And so now you can see that if I take d dt of this term, I'll have the divergence of du dt. And if I take the divergence of this equation, I'll have rho naught times the divergence, or I can change the order. It's the divergence of du dt. So this term and this term will now be equal. So I can replace this term by, when I've taken the divergence, by this term on the right-hand side. So the divergence of that gradient of rho prime becomes del squared rho prime, and this ddt gives me a d2 rho prime dt squared, and I'll have an a naught squared. So that's a familiar equation to you. Taking ddt of the first term and the divergence of the second term gives this equation for d2 rho prime dt squared is equal to a naught squared del squared rho prime. And that's, of course, familiar to you. That's the wave equation. So that is why these equations, the equations of fluid mechanics, reduce to the wave equation. So let's go on for there, or since S is a constant and U is equal to 0 initially at t equals 0.
How do you go, that's quite extraordinary to me, and obviously true, but what was your feeling? How did you know to take the time derivative of the first equation and the divergence of the second?
Oh, well, that's clear because, but that's a good question. Why did I take the divergence of the ddt of this term? Because I want to make this term exactly equal to this term.
Right, so that's what drove your...
So that drives it.
Yeah.
And then so I can replace in this equation the divergence of this equation. And so I'll put it on over here, it'll be minus, and then take it to the right-hand side, it'll be a naught squared del squared rho prime.
Yeah, now you have no explicit dependency on the density.
That's right,
It's nice.
because the density is second order.
Yeah. Well, pretty good.
So that's really tremendously significant. And it's going to lead us on to think about a whole lot of things, and you'll see why I'm doing it. Because it actually gives you a lot of insight into all kinds of problems that are real. And how would you do it, and so on and so forth. So you get the wave equation out of the equations of fluid mechanics. That's an important realization.
Who first found that?
Oh, good God, I have no idea.
It wasn't you though, right?
Oh, no. It would have been Lord Rayleigh, probably. You know, these Lord Rayleigh and maybe Horace Lamb, they recognized these connections. But I want to make these connections because I'm going to do something important for you in a minute. So just hang on for a while. But I want to do something here that's important. Since S is a constant and U equals 0, and the curl of U is equal to 0 at t equals 0, namely I got U everywhere, so I take derivatives of it, curl of U is obviously 0 at t equals 0, then Kelvin's circulation theorem, or something that I just illustrated physically at the time, since the pressure acts normally to the surface, it can't introduce any torque and it can't produce any vorticity. So the curl of U at all subsequent times, the curl of U is equal to 0 at all subsequent times because the curl of U is the vorticity. And if the curl of U is identically 0, then it's satisfied, it's necessary, or it's sufficient for U to be the gradient of a potential, but it's also a theorem of mathematics that it's necessary that U is a gradient of the potential. So now, let's go back up to that first equation, which was rho du dt, rho naught du dt. So that will be, if I have U as the gradient of the potential, it'll be the gradient of d phi dt because I can reverse the order of the differentiation. So rho naught times the gradient of du dt is equal to minus dp, the gradient of the pressure, which is minus a naught squared gradient of rho prime, which is minus the gradient of the pressure. So you can combine these two, take the minus grad p to the left-hand side, and we'll see something important, that we get that p prime is minus rho naught d phi dt because it has to be 0 for all times. So p prime is minus rho naught d phi dt, and U is the gradient of phi. So p prime and U are derivable from one function only, the velocity potential. So what is the equation for the velocity potential? Well, it's the wave equation, of course. Rho prime is minus rho naught over u squared. So I have rho prime is minus rho naught over a naught squared d phi dt. So from continuity, if I put ddt of that into the continuity equation, I get minus rho naught upon a naught squared d2 phi dt squared plus rho naught del squared phi equals 0. Now, that is a very significant equation because you can divide by a rho naught here, and you've got 0 on the right-hand side. So you get the wave equation for phi. Del squared phi is equal to 1 upon a naught squared d2 phi dt squared. So now what I want you to understand is that let's suppose a naught went to infinity. The speed of sound went to infinity. Then the right-hand side is 0, and I have del squared phi equals 0. But that would... So now, if a naught goes to infinity, you have the other part of this course, the incompressible fluid mechanics, del squared phi equals 0. But you can also see in this equation here that this left-hand side will be like phi over, if you had a point source, it would be like phi upon r squared, and this d2 phi dt squared would be like omega squared times phi over a naught squared. So omega over k is a naught squared. So this is k squared times phi, and this is 1 upon r squared times phi. So if I want this term to be 0, it requires kr to be much less than 1. Now think about that. So that's k is 2 pi on lambda, right? So that's, I'm saying that if r upon lambda is much, much less than 1, then this equation, this wave equation, reduces to del squared phi equal to 0. So now let's go back to my submarine problem that I told you about, where every time the blade goes around, I get a cavitation bubble, and the bubble expands and it collapses as it goes around. And then I get the next blade, and the bubble expands and collapses. So let's suppose that occurs, the frequency, the blade passing frequency is 10 hertz. So what's the wavelength in seawater? Come on. What's the speed of sound in seawater, roughly? Nobody got any idea? It's about, the speed of sound in water is about 1,500 meters a second. 1,500 meters a second. So if the frequency is 10 hertz, what's the wavelength? The speed is f times lambda. Come on. What's the wavelength? Nobody can guess. 1,500 what? Divide by 10 is how many? 150 meters. So let's suppose you had a microphone that's a kilometer away from the submarine. What would you be hearing? The near field or the far field? No, if you were a kilometer away, you'd be hearing the far field. You'd be hearing the acoustic field. But if your microphone was only 20 meters away, what would you be hearing?
The near field is defined as what, within one wavelength then? Or?
Yes.
Oh, okay.
because here, what I just said, see this, the right-hand side is negligible if r upon lambda is much, much less than 1. So the key non-dimensionalization is the wavelength. So I can ignore this right-hand side here, and I just got del squared phi equal to 0, as if water were incompressible, if I'm in the near field. Namely, r is much less than a wavelength. But if I'm in the far field, r is much larger than a wavelength, and the wavelength is, we just worked out, at 10 hertz, the wavelength is 150 meters. If I'm far, far away compared with 150 meters, what equation have I got to solve? Not this equation, del squared phi equal to 0. I've got to solve the wave equation. And what I'm going to hear is the wave, the acoustic wave in seawater. So that's a very important insight.
What do you hear in the near field then?
I hear a pressure fluctuation, but it's an incompressible pressure fluctuation, as if the speed of sound were infinite. So it's the same pressure fluctuation, only attenuated because of the R squared law. It's the same pressure fluctuation I felt on the hull of the ship that drove the ship to very large amplitude vibration. So it's correlated over the back end of the ship, because forget the wavelength's huge, so it's an instantaneous pressure field, as if the speed of sound were infinite. Del squared phi equals 0 in the near field. But the near field becomes ultimately, for large R, the far field. And the far field is an acoustic field. Right? So that's a very important insight.
Can you describe what you hear in the far field then? You just hear wave.
You'll hear sound. If you could hear like a sonar can hear, you'd hear the acoustic field from this submarine 2 miles away with a blade that's cavitating. And the only blades, that's why people who develop submarines spend a lot of time trying to avoid cavitation. I don't want to have a monopole. So if you're thinking about an electrical analogy, if I have a monopole, so now I don't have a fluctuating charge in the electrical analog, but I have a dipole, which is a plus and a minus close together, and they can oscillate. And that's a dipole. And that would be the equivalent here, would be a dipole source, which would be a source and a sink close together, like a sphere, like an oscillating sphere, like a fluctuating, and an oscillating sphere is a fluctuating force. So a fluctuating force on the propeller, even if it doesn't cavitate, will in the far field look like a dipole. For the equivalent electrical analog, where you have a charge surrounded by an electron cloud, but if the electron cloud moves with respect to the nucleus, it looks like a dipole, a source and a sink close together, and they oscillate. Okay, so now I want to do something for you. I want to talk about the solution of the wave equation. So let's do it in the simplest case first. Let's work it out in one dimension. So I'm imagining a one-dimensional acoustic propagation inside a duct, just one-dimensional for a minute. And I'm solving the wave equation. So most of you would know that the solution to the wave equation is rho prime is f times a function of x minus a naught t plus g of x plus a naught t. And that is obviously a solution of the wave equation because d2 rho dx squared would be, if I differentiate this, I'd differentiate it with respect to this argument here, and then differentiate the argument with respect to x, and I get 1 for that. So differentiating it with respect to this argument is f double prime, and this will be a g double prime. That's d2 rho prime dx squared. And what is d2 rho prime dt squared? Well, if I differentiate this with respect to itself, to its argument, it's f prime first, the first derivative, and then the next one is going to be a double prime. But when I differentiate this argument with respect to t, I get a minus a naught and a plus a naught. But then I got to do it twice, and I get a minus a naught all squared, which gives me a plus a naught squared and a plus a naught squared. And so I've automatically satisfied the wave equation. So you say, well, that was easy. I've created a solution of the wave equation that's sort of trivial in a way. And it turns out that it's the most general solution of the wave equation because it contains two arbitrary, not two arbitrary constants, two arbitrary functions. So it's a very general solution. Now I want to do something a bit tricky. I want to interpret that solution physically for you, because it motivates what I'm going to do in a minute. So the physical interpretation, let's do it in the simplest case, and we'll imagine that g is equal to 0, and we've only got this term over here, f of x minus a naught t. Well, now that introduces something very important. It says that rho prime then varies with x and t in such a way that rho prime is a constant when x minus at is constant. That is, on a characteristic curve, if x minus at is a constant, and suppose it's x naught, then x is equal to x naught plus at. So that's called a characteristic curve, and we're only going to do elementary characteristics, where I'm not going to do the full-blown nonlinear characteristics, but it surely helps to start simply like this. So on the characteristic curve, x is equal to x naught plus at, rho prime is given by rho prime at x naught. Now, because x minus a naught t, x minus at is x naught, so this function is simply this right-hand side, x minus a naught t is just x naught, and so rho prime is going to be always the value that it had at t equals naught, at x naught. So now that is stated in words here. So on a specific curve, and it's called C+, on this specific curve, x is equal to x naught plus at, so on C+, rho prime has the value that it has at x naught. So in general, since u is d phi dx, the most general solution for u is f of x minus a naught t plus g of x plus a naught t, since u satisfies the wave equation as well. And the solutions for rho prime and u are related simply from continuity. This was our reduced conservation of mass equation. So we've got in general that rho prime is f of x minus a naught t plus g of x plus a naught t. So d rho prime dt is minus a naught f prime plus a naught of g prime. And this is, if u is equal to f of x minus a naught t and g of x plus a naught t, then plus rho naught. So this will be the derivative of f prime with respect to this argument times the derivative of the argument with respect to x. So that's plus rho naught f prime plus g prime equal to 0. Where f and g are arbitrary and the equation will be satisfied, this equation will be satisfied at all times if this term and this term sum to 0, or let's see how that goes. So so if f prime, if that is equal to rho naught over a naught f small f prime, if that's true, and if g prime is equal to minus rho naught over a naught g prime, then I've satisfied this equation equal to 0 for all times. And that says that I can integrate these things, and I can say that f over a naught is f, big F over rho naught. And I can choose my constant to be 0 because I don't want a constant velocity. And the same thing over here, g over a naught is capital G minus capital G over rho naught. Now that's very helpful because that enables us to define a new f bar, which is simply 1 upon a naught times f of x minus a naught t. There should have been a t in there. And g bar is g over a naught. Then u over a naught is f bar x minus a naught t plus g bar of x plus a naught t. And rho prime is f bar, rho prime over rho naught, I mean, is f bar of x minus a naught t minus g bar of x plus a naught t. All right. That is interesting now because I can combine these things, and here's how you do it. I can change this rho prime to a p prime because p prime is a naught squared rho prime. And so now if I add these two equations, this will go out. So I'll have rho prime over rho naught plus u over a naught is equal to twice this. So u over a naught plus rho prime over rho naught is 2f bar x minus a naught t. And if I subtract the two, u over a naught minus rho prime over rho naught is this minus that is 2g bar because these cancels. These cancel. And then if I write rho prime is p prime over a naught squared, then I can rewrite these two equations. I multiply throughout by rho naught a naught, and I'll have a, but I want to get an a naught squared rho prime here, so I've got to multiply by rho naught and then an a naught squared. And if I do that, I get finally the equations that I want to show you, that one of them is P minus P naught plus rho naught A naught U is 2 rho naught A naught squared F bar on X minus A naught T, which is 2 rho naught A naught squared F of psi, which is a constant for psi equal to a constant. So if X minus A naught T is equal to psi, then X is equal to psi plus A naught T. So, X minus A naught T is equal to psi, yes, so psi is equal to X minus A naught T. Or X is equal to psi plus A naught T. So it says on a particular curve C plus given by X is equal to psi plus A naught T, P minus P naught plus rho naught A naught U is equal to this constant on the right-hand side. And that is the method of characteristics. And I have a similar equation for the other equation. Similarly, P minus P naught minus rho naught A naught U is minus 2 rho naught A naught squared G bar of eta, which is a constant for eta equal to a constant that is on the curve C minus given by X eta is equal to X plus A naught T. So X eta is equal to X plus A naught T, or X is equal to eta minus A naught T. Then P minus rho naught A naught U has a constant value which is given by the value it had at T naught when X was equal to eta. So that is, I'll illustrate that next time. So here is a statement of what it is in words. So on this C plus, P minus P naught plus rho naught A naught U is equal to this right-hand side. On C plus, which is X is equal to psi plus A naught T, and P minus P naught minus rho naught A naught U is equal to minus 2 rho naught A naught squared G of eta on C minus, which is X is equal to eta minus A naught T. And that is very, very powerful. And I'm going to do it next time, perhaps, or maybe I'll just start. How do you use this? So you can follow through all this mathematics, but how does it actually get used? And what can I physically understand because of it? So let's suppose I have this wave in a tube, and you've seen me do this already. I give this piston here at the left-hand side a constant velocity, but now I have a closed end here. I worked out what would happen if I didn't have a closed end. I'd send off an acoustic weak shock wave, you'll recall. So it's just an acoustic wave that went off downstream here, propagated at basically the speed of sound, A naught, and the pressure was higher behind the wave. Well, let's see what actually happens. Let's suppose I work this case out with a closed end here. What do you think happens? What do you think happens? What do you think will happen? What do you think will happen at that closed end? Will it be different if it was an open end? Yes. And the good question is, why? What actually, how can I understand what happens? How do I do it? So let me work it out here for you. So I've drawn the piston velocity here. Here's the piston moving at constant velocity, starts here at t equals 0 and moves at constant velocity. X is equal to up times t. And now let me draw some characteristics. So I'm going to, here's a c plus, x is equal to c plus a naught t. And here is a c minus, which is x is equal to eta, for example, or psi 2 minus a naught t. So, on all the c minuses beginning on at t equals 0, so here, on x between 0 and L, so it's easy to work out, P minus P naught minus rho naught A naught U on all of those, well, on all of these C minuses, what is the value right here? Well, the velocity is equal to 0 and the pressure is equal to P naught. So this constant has to be 0. And all C pluses in this region here, beginning at T equals 0, on between 0 and L, P minus P naught plus rho naught A naught U, is equal to a constant, but P is equal to P naught and U is equal to 0, so that constant must be 0. So let's go to this point here where this one, the C plus and the C minus intersect. And where they intersect, they must have the same value. And so where they intersect, I'd have this one, and so if I added the two, these will go to 0, and so P was going to be equal to P naught, and U was going to be equal to 0. So everywhere in this region here is where I can reach any point in here from a C minus and a C plus. So in this region here, everywhere, I could have a C minus and I could have a C plus, and they would give me 0 velocity and 0 pressure. However, what happens in this region 2? Well, on this region, in this region 2, let me take this C1 minus from here and go back here to 1. So now what happens? Yeah, so I've done that. So in region 1, the pressure's P naught and U is equal to naught. Now we're going to take the C1 minus is coming back from the piston. So P minus P naught minus rho naught A naught U is equal to naught. So at 1 on the piston, so at this point here, I now know what the piston velocity is. So I'll put that in, and I'll get what the pressure is at 1. And so I can do it. So at 1, P1 minus P naught minus rho naught A naught, and I know what the velocity is. It's the velocity of the piston, is equal to 0. So on the C1 plus now, that goes through that 1, that point 1, so here's C1 plus. I want to work out what happens along this characteristic. So I want the constant value for this characteristic. So I can do that. So on the C1 plus, at 1, P1 minus P naught plus rho naught A naught U P, because that's what the velocity is at 1, is a constant. But P1 minus P naught is equal to rho naught A naught UP. So the constant must be, I can put that in here, I can put that in there, and the constant must be 2 rho naught A naught UP. So I know a lot now. Thus at point 2, the intersection of the C2 minus and the C1 plus